Hello and welcome. My name is Gareth Lloyd. I'm MC for this webinar from the Global CCS Institute. A warm welcome from us. This is one of a series of webinars that we arrange on key topics in CCS involving speakers presenting the latest developments on CCS. So as I start, and in a moment I'll introduce our speakers, what I will do is just go through a couple of housekeeping arrangements. So if you bear with me one moment, we will move on to the next slide. So you will see on the right-hand side the little box for questions. What we're keen to do is to take your questions during the presentation. Myself as MC will then pose them to our panel, which is 4, at the end of the presentation. So please do put your questions as we go into the little box, into the control panel. We'll pick them up. We will, on some occasions, combine perhaps 2 questions that are very similar just for effective use of time. So this is a seminar from National Grid on shared capacity and based on the experiences that National Grid has had in this area. I'll introduce our 2 presenters, and that is Calum Hughes and also Dave Bevan. So I repeat, please ask questions as we go by putting them into the little box. And I would encourage you to do so because that makes the most of the interactive session that we've got. So I will at this point stop and I will be now handing over to Calum and Dave, who will give the presentation from now on. Thank you.
Thank you, Gareth, for that kind introduction. And thank you also to the GCCSI for supporting the report upon which this webinar is based. The work that the GCCSI does in supporting and developing, supporting the development and sharing of CCS expertise and knowledge is invaluable for those of us in industry working to get projects off the page and into reality. I would also like to say hello and welcome to everyone who is listening in, wherever you may be, and thank you for taking the time to participate today. If you have already looked at the report, then I hope you found it thought-provoking and useful. If you haven't yet got a copy, then it is available for free download on the GCCSI's website. Before I start looking at the report, just a few words about National Grid, what it does and why it's involved in CCS. National Grid owns and manages energy grids. In Britain, it runs systems that deliver gas and electricity across the entire country, and in the northeastern states of the US, it provides power directly to millions of customers. National Grid holds a vital position at the centre of the energy system in these countries, where its infrastructure joins everything up. National Grid has around 26,000 employees and over 10 million customers, so we are very aware that we provide a service to society, and that we are at the heart of one of the greatest challenges facing that society, the creation of sustainable energy solutions for the future. For this and other reasons, National Grid, via its European Business Development Group, invests a great deal of time and effort to apply its expertise in high-pressure gas pipelines and long-distance gas transportation generally to help the CCS industry grow safely and successfully. As part of this effort, National Grid has established National Grid Carbon, an organisation dedicated to CCS transportation and storage development. Via this organisation, National Grid is a member of the groups leading both the Don Valley Power Plant and White Rose CCS projects in the UK. I shall now hand over to my colleague Dave Bevan, who will describe these projects in a little more detail.
Thanks, Calum. As Calum mentioned, part of this effort, NGCL, National Grid Carbon Limited, has developed the Yorkshire and Humber Cluster CCS Transportation Storage Network. And this network comprises of approximately 80 kilometres of onshore 24-inch dense phase pipeline an approximately 90 kilometres offshore pipeline leading to an offshore platform facility that will allow storage into the national grid Ceylon aquifer of 542. This system will be able to transport up to 15 million tonnes per annum of CO2 and currently supports Tuco's Don Valley Power Project and the White Rose Project at Drax Power Station. A multi-junction, as you can see on the map, will be located near Campbellsforth that would allow the input of further supplies of CO2 from the surrounding area. There are large amounts of existing and planned generation assets in the Yorkshire and Humber area, leading this area to be a perfect choice to demonstrate the effectiveness of a multi-user system. A second phase to the onshore pipeline would be a South Humber Bank pipeline to enable connection of further key industrial and generation assets. The new pumping station at Barmston at Bridlington Bay will enable the pre-compressed dense phase CO2 to be increased in pressure to approximately 884 bar. This should allow sufficient pressure to inject the CO2 for permanent storage into the Ceylon aquifer. The offshore facilities will be a base case developed with no regrets infrastructure to allow growth. This includes an offshore multi-junction that would allow connection to enhanced oil recovery sites and further aquifers. This also has potential for further input into the 542 aquifer. That is basically a summary of our multi-user system. I'll hand back to Calum.
Okay, thank you, Dave. So moving on to the report itself. Firstly, may I ask you to please read this disclaimer and also take particular note that the case study set out in the report is entirely hypothetical. And whilst we have used our project development models to produce the cost data on which some of the examples in the report are based, none of the data or information presented appertains to any actual project. I would specifically counsel against any attempt to extrapolate or interpolate any of the data presented in the report for the purposes of cost or price estimation on other projects. With regard to the global applicability of the report, the examples and discussions presented are based upon UK and European legal and regulatory frameworks, but the issues identified and discussed should be relevant when developing a CCS transportation and storage system anywhere in the world. Regarding the rest of today's presentation, the report is relatively lengthy, so in order to allow sufficient time for Q&A, I'll explain the content of each section of the report at a very high level and spend most of the short time available highlighting a few key points. In synopsis, these points are that the sharing of optimally sized infrastructure could significantly reduce the cost of CCS, that the development of optimally sized infrastructure could be incentivised by using a well-designed capacity charging mechanism, and that the design of a capacity charging mechanism is likely to be significantly affected by the prevailing legal and regulatory framework. So moving on to the content of the report then, Part 1 incorporates Sections 2 and 3. Section 2 suggests and discusses a range of issues which should be taken into account by developers of CO2 transportation and storage infrastructure. Of these, the one I would like to highlight today is the issue of why the development of shared infrastructure systems should be advocated. When considering this point, we should consider why CCS projects are not progressing to sanction as quickly as required. As it becomes increasingly unlikely that there are any insuperable technical barriers to CCS development remaining, and the legal and regulatory frameworks required for CCS to be developed and operated begin to be put into place, the primary remaining barrier to the progress of CCS projects appears to be the need to produce a viable commercial case for the development of those projects. An important question is therefore, how can the commercial case for CCS projects be improved? One obvious way is by reducing costs, and this can be achieved to significant degrees by capturing the economies of scale which accompany the sharing of infrastructure. Put simply, the cost per unit capacity of developing and operating a single large capacity infrastructure system is lower than the aggregate cost of developing and operating separate smaller capacity systems which collectively provide the same total capacity as the single large system. This may seem a simple and intuitive, even facile point, but it may be fundamental to the timely development of CCS. Analysing this point in a little more detail, there are two components to the available economies of scale. These can be identified using this simplified curve, which describes how the aggregate cost of capacity in an infrastructure system increases as the capacity of that system increases. The point at which the curve crosses the vertical axis represents the fixed cost of developing the system, to which the curve relates. Whatever its actual capacity, if the system is built, then when calculating the charge per unit capacity, these fixed costs will be divided across the total capacity of the system. Therefore, the larger the capacity of the system, the smaller the amount of the fixed cost that will be allocated to each unit of capacity, and hence the lower the cost of each unit of capacity will be. This is the first available economy of scale. It can also be seen that the gradient of the curve reduces as the capacity of the system increases. This indicates that each subsequent incremental unit of system capacity costs less than the previous. Therefore, the larger the capacity of the system, the lower the average cost of each unit of capacity. This is the second available economy of scale. These economies of scale can be captured by developing large multi-user shared infrastructure systems. And whilst it is true that this strategy increases the absolute cost of the initial infrastructure system, this must be balanced against the consideration that, provided that it's correctly sized, a shared infrastructure system will reduce the total cost of system capacity, and therefore CCS, to all system users, and thereby to society as a whole. And it's worth mentioning here that there are a number of other societal reasons to build large multi-user infrastructure systems. They reduce barriers to entry to new system users by ensuring the provision of CO2 disposal at a known price, thereby facilitating the use of CCS with the associated reduction in CO2 emissions. They reduce environmental and community disruption and cost by avoiding the need to construct multiple pipelines and associated onshore infrastructure. And they create and protect industry and employment in the region they serve by providing a facility via which large emitting industries can reduce their carbon costs and hence increase their competitiveness. The other item from section 2 which I will quickly highlight is that of third-party access. Regardless of where their project is situated, CCS developers will need to take cognizance of any legal rights given to third parties seeking access to the scheme that the developer is pursuing. In the UK, these rights are provided by way of regulations which transpose the European CCS directive into English law. The UK regulations themselves are largely based upon the well-established rules which govern third-party access to oil and gas infrastructure in UK waters. But regulation will vary from jurisdiction to jurisdiction, even within the EU. Nevertheless, it is likely that in all jurisdictions, third-party access regulation will have a significant effect upon the design of capacity charging mechanisms, and that authorities may be granted powers to require changes to the design of the system, potentially even after development consents have been obtained or construction has started. Section 3 of the report presents a hypothetical case study which is used as the basis for analysis throughout most of the remainder of the report. This schematic shows the components of that system. The scheme incorporates a CO2 collection hub, a shared onshore and offshore pipeline connected to an offshore storage site comprising a jacket and topside, and a number of injection wells. The scheme has 6 system users, and it is intended that between them they should demonstrate most of the potential characteristics which a system user might have. Of course, in reality, a system might have any number of users with any combination of the characteristics identified. System user number 1 is a fossil fuel powered electricity generation plant with its own CO2 export compression. System user number 2 is an industrial CO2 generator without its own CO2 export compression plant. System user number 3 has acquired a system input facility at the transportation systems flow collection hub. It should be noted that this user may be a physical or a non-physical user or investor. System user number 4 has acquired a system input facility away from the transportation system's flow collection hub. Again, this may be a physical or non-physical user. System user number 5 has acquired an input facility at the offshore hub and will be a user of the storage site only. And system user number 6 has acquired a takeoff facility at the offshore hub. Part 2 of the report deals with the provision of connection assets between the system user's plant and the shared infrastructure system. A relatively simple and intentionally generic scheme is described in a form similar to that which might be seen in a gas transmission system's connection and use of system code. The connection charge example presented assumes an annual charge made in arrears over an agreed payment period, which comprises capital repayment and a rate of return on the capital investment made by the system developer, plus an annual operations and maintenance charge. Many variations on this theme could equally well be applied. This area is fairly straightforward, and the example presented is intentionally based upon a proven model. However, there are 1 or 2 CCS-specific technical points which may be worth noting. Firstly, fiscal quality, mass transfer and composition measurement of high flow rate, high pressure CO2 is novel, and there is therefore inherent risk in taking responsibility for performing these functions. Secondly, the specification, monitoring and control of solids content in the fluid stream entering the shared system has the potential to be an unusually important issue in CCS systems due to the potential for the blocking of the reservoir near the wellbore and the high cost of both well rectification workovers and offshore filtration systems. And finally, the integration of control and safety systems on shared dense phase CCS infrastructure will require considerable thought, particularly with regard to inter-system executive actions, for example between the infrastructure's SCADA and the user's plant control and safety system. Part 3 of the report deals with charging for the use of shared CCS infrastructure and is in 4 sections, 5 through 8. The report proposes that there should be 3 separate shared system charges, and sections 6, 7 and 8 each deal with one of those charges. These sections are like part 3 in the form which reflects a generic use of system code. Section 5 discusses why the 3 separate charges are proposed and how allocation of costs between the different charges might be used to influence investment in and take-up of system capacity. How the allocation of costs to charges might be influenced by regulation is also discussed. I will concentrate today on section 5, and in particular how investment in and demand for CCS infrastructure capacity might be affected by the number of charges used to recover the costs of developing and operating the system, the design of those charges, and the way in which the costs to be recovered are allocated to them. Firstly, let's look at the costs which must be recovered. This slide shows the broad categories of costs which apply to CCS transport and storage infrastructure in Europe. The contents of the list would be typical for any large infrastructure project, with the exception of the financial security and post-closure obligations cost categories, both of which are CCS specific as they stem from the provisions of the European CCS Directive. They are applicable only to projects in the EU, but it is likely that similar costs will be relevant in many jurisdictions. All of these costs must be recovered by the system operator via one or more charges. One possible combination of heads of charges is shown here. In practice, the number and design of the charges will be influenced by the applicable regulatory framework, but it is suggested that this set of heads aligns with the regulatory framework which currently prevails in the UK. Broadly speaking, the EPC charge recovers CapEx and is the charge for having the capacity required built. The capacity rights charge recovers fixed OPEX and is the charge for acquiring the right to use a certain amount of capacity in the system. And the use of system charge recovers variable OPEX and is the cost of actually using capacity in the system. This said, it is important to recognise that there is flexibility in how costs might be applied to each separate charge. It may seem counterintuitive that there should be a separate EPC charge and capacity rights charge, but a party acquiring the right to use system capacity may not always have procured its development, and a party procuring the construction of capacity in a system may not always wish to acquire the rights to use that capacity for the full life of the system or at all. In addition, it may be desirable to have the ability to allocate costs in certain ways that would not be possible if a single charge covering all of the relevant costs was to be adopted. Alteration of the allocation of costs to the different heads of charges could be used to influence the behaviour of potential investors in and users of a CCS infrastructure system in a number of ways. A few of these are shown on this slide. Regarding the first point, the capacity rights and use of system charges may expose the system operator to varying degrees of demand risk. Therefore, the magnitude of this risk will be increased if the extent to which costs are recovered by these charges is increased. On point 2, as we will see in a moment when we look at part 4 of the report, depending upon the way in which costs are allocated across system users, it may be that some would pay a higher price per unit of capacity they procure to be developed than others. Where this is the case, the allocation of costs to the EPC charge will tend to increase that weighting. The explanation of point 3 is similar. If state funding is being used to subsidise the development of assets, then if costs are allocated to charges paid by system users via the capacity rights charge and the use of system charge, then this has the potential to reduce the burden on the state coffers. The penultimate point stems from the potential that different returns may be permissible on different charges. For example, returns included in the EPC charge may be restricted to true incremental cost, whereas it may be permissible to make a reasonable profit on the costs included in capacity rights and use of systems charges. And finally, in the case of agreements where payments may be calculated based upon a percentage of a particular charge, for example, a capacity option agreement may have an option fee calculation based upon the relevant system EPC charge, the allocation of costs to that charge can be used to affect the costs of options and therefore the likelihood of option take-up. The extent to which cost allocation might affect the level of charging is illustrated by these figures. I will not read out all of the text, but in summary, option 1 maximises the EPC charge, option 3 minimises it, and option 2 is a mid-ground. Option 1 therefore loads cost onto the parties paying for the initial development of the assets, reducing the cost for other system users and probably reducing demand risk on the system operator. Option 3 does the opposite. The numbers shown are from the 2 user system example set out in the report, and the 2 columns show the costs allocated to the 2 users. Hopefully you can see that the total allocation of cost to each user does not change across the 3 options, but that there is a very large change in the level of the 3 charges. It should also be noted that although the numbers are labelled as charges on the slide, they are in fact only a summation of costs. Therefore, if different rates of return were to be applied to the different costs in order to arrive at the actual charges levied, as may well be the case, then the variation of the cost allocation across the 3 charges shown could have a significant effect upon the system user's aggregate costs and the system operator's return on investment. The final part of the report, part 4, deals with the allocation of costs between multiple system users. It's important to emphasise that this is not the same as the allocation of costs to different heads of charge, which we have just looked at, but that the two can interact to affect the risk and cost distribution across system users, as well as cash flow, aggregate project returns, and other financial and commercial aspects of the venture. The concepts presented in this part of the report are very closely related to the economies of scale argument for constructing shared infrastructure, which I outlined earlier. This is because the flexibility to allocate costs to different system users is based upon altering the distribution between those system users of the savings gained from the economies of scale, which are inherent in a multi-user system. So to reiterate the two areas of economies of scale, this slide shows again a curve for a hypothetical infrastructure project describing how the aggregate cost of capacity increases as the capacity of the system increases. The point at which the extrapolated curve intersects the vertical axis gives the cost of providing the hypothetical infrastructure system with a capacity of 0. Of course, a system with 0 capacity cannot be built, but whatever the capacity of the system actually built, this component of the overall cost remains fixed. It is the capacity-independent cost. As the capacity of the system increases, the capacity-independent cost is spread across an ever larger number of units capacity, and this reduces the cost of providing each individual unit of capacity. It can also be seen that as the capacity of the system increases, the gradient of the curve decreases. This indicates that each additional unit of capacity costs less to provide than the previous. The savings achieved via these economies of scale might be distributed between the users of the system in a number of different ways in order to incentivise the desired investment in and take-up of system capacity. This slide shows a plot of the EPC costs for the development of the report's example project. Each data point represents the cost of developing the system for a different number of system users and hence with a different capacity. The costs are calculated using National Grid's in-house costing data and estimation methodology. It can be seen that the fitted curve has a similar form to the theoretical example on the previous slide. You may notice that the cost of each individual system design does not lie exactly on the curve. This is because the actual increase in system cost with increasing capacity is not smooth due to technical factors such as standardized equipment sizes. Nevertheless, it is suggested that a smooth curve, as shown, fitted using an agreed method, could be used to derive incremental costs of capacity as part of a transparent and non-discriminatory capacity charging mechanism. And here we can see the variation of cost distribution that would result from a range of 11 different cost sharing mechanisms. There is no time today to consider all of the cost sharing mechanisms depicted, but hopefully considering mechanism 1 and 8 will be sufficient to demonstrate the significant effect which the application of different cost allocations can have. Under mechanism 1, the user for whom the system is primarily developed bears all of the capacity-independent costs, and each subsequent system user pays only the true incremental cost of the capacity it acquires. Under mechanism 8, the total system costs are shared equally across each unit of system capacity, and each system user pays the average cost per unit capacity for the capacity it acquires. Broadly speaking, mechanism 1 may make it more difficult to secure sanction for the development of the system initially, but once sanction was secured, it would lead to the development of an optimally sized system with the maximum number of users acquiring capacity. Mechanism 8 would have the opposite effect. It is suggested that in a scenario where the cost of the system's first user are state subsidized, that a mechanism closer to mechanism 1 would be the most sensible from a macroeconomic point of view, as it would incentivize, with the use of public funds, the development of a large capacity system with the societal benefits I've already mentioned. Well, that covers all the sections of the report. There's more detail in the report itself, but as I said, because of time constraints, I've only been able to emphasise a few key points today. To reiterate these, a major barrier to the development of CCS projects is the difficulty in producing a convincing commercial case. The sharing of transportation and storage infrastructure costs could significantly reduce this barrier. The larger the capacity of the system, the greater the beneficial impact. The mechanism for calculating the charge that each user of the infrastructure system pays for their acquisition of the capacity in and use of the system could be used to influence investment in and take-up of capacity in that system. And the design of such a capacity charging mechanism is likely to be significantly affected by the legal and regulatory framework prevailing in the relevant jurisdiction. Well, that's the end of the presentation of the report. I hope you found it informative and interesting. Thank you again for listening, and we look forward to hearing your questions. I'll now hand back over to Gareth.
Thank you very much, and look, I'd like to thank our presenters for a very clear exposition in a quite short period of time with a lot of insights on the topic. So what I'm going to do now is present those questions that you are hopefully continuing to add to your boxes to our presenters, and I'll just briefly explain our panel of 4 from National Grid. Calum Hughes has been on the National Grid CCS team for 3 years. He's an upstream oil and gas industry specialist involved in designing and building production plant and infrastructure. Dave Bevan is part of the carbon capture commercial development team in National Grid Carbon. Johnny Horsford is project director with the National Grid Carbon CCS team, and he's focused on the carbon dioxide transportation infrastructure and has been working on CCS for the last 4 years, including leading National Grid's participation with the Don Valley project, which I'm sure our audience will have heard of. And Paul Sullivan's commercial lead for the Humber CCS cluster with National Grid and responsible for securing the agreements for the initial support and funding from the United Kingdom government. So a well-rounded panel, and what I will now do is pose these questions to our panel. I'll ask them to take those in order. So first question that we had about halfway through was, what is the EPC charge? How could the charging model be applied to other network hub projects? So, team.
The EPC charge is the component of the overall charge that a system user would pay for its capacity in a system, which is used to recover the costs of the engineering, procurement, and construction of the part of the capacity that system user has procured. So I mentioned in the presentation that some flexibility, potential flexibility about what goes into the EPC charge, and I'm thinking about some things like ongoing CapEx. Would that be considered as OPEX or CapEx? Decommissioning charges, would they be considered as OPEX or CapEx? And several other costs, rather than charges. And they could be put into the EPC charge and charged in essence up front, or they could be put on either of the charges which are associated with the use of the system.
Okay, thanks. And look, the next question is, and I know you introduced this by talking about it was specific, obviously, to United Kingdom. Can you see any region-specific parameters that would significantly change the results from your model? Probably a little bit difficult to do that hypothetically, but some insight to that would be welcome.
Region. Well,
you know, for example,
yeah.
United States or whatever, North America rather than Europe. That may be a bit of a hard question for you because it's not your focus.
No, it's not the jurisdiction I've looked at. But what I would say is that what we tried to do in writing the report was to both give an insight into our direct experience, which is in Europe and the UK, but also to try and discuss points and areas which we felt were likely to be relevant in many, if not all, jurisdictions. So what I would say is, if the questioner is asking, could I say things would be different in the US because of X, then I'm unable to do that. But what I would say is, if I was developing a shared infrastructure system in, for example, the US, then I would want to consider the same points that were brought up that are set out in the report for that jurisdiction.
Okay, that's fine. And a different kind of question here, have you considered various options for long-term liability allocation? How does this influence the results?
Okay, I think if Paul's on the line, this might be one for him.
Yep. Paul?
Yeah, Calum, hi, good morning everybody. I think in terms of long-term liabilities, yeah, as Calum mentioned in the presentation, there are a number of ways that systems can be developed. Clearly in the UK there's an active programme to try and get UK government funding. That may well deal with liabilities in a particular way as opposed to a fully, let's say in inverted commas, commercial system that may deal within a different way. The particular issues that we're sort of struggling with in terms of how this might pan out for our particular project is around the CCS directive and the way the financial securities provisions might work. So it may not be applicable to all the methodology that Calum's outlined and where we might eventually end up may not be replicable, of course, because different jurisdictions will have different financial securities. But the essence is that we will obviously in a charging mechanism will have to recover those liabilities, but it will be for the operator of the store to manage that situation into the long term with the final hand back to the authority.
Okay, thanks. And can you say anything from our panel about how costs for later expansion of the system might be best allocated? Should these be borne mainly by new users?
That's a really interesting question, and it highlights the fact, or it highlights the point that there may be a conflict between what the system operator would like and what the regulation, the regulated framework would allow. So third-party users coming to the system after it's built, or perhaps also worth thinking about after it's been consented or after construction has started, may be given legal rights to acquire capacity. And the way that the costs of providing that capacity can be recovered are likely to be governed by regulation. If they're not, and well, certainly in the EU, that seems to be necessitated by the requirements of the CCS directive, and certainly where other large nationally important infrastructure systems are privately owned, there are regulatory frameworks in place to ensure that third parties can acquire access to them.
So sort of a supplementary question to that is, can you see a situation where those that are involved at the inception stages could be disadvantaged compared to those that come along, you know, several years later, and you know, and how that's treated within a regulatory framework?
Yes, again, an excellent question. The issue of first mover disadvantage is a big one, and it goes to the heart of what I was saying. I think in one of my final slides, is that if you try and charge all users average cost, then smaller users won't be able to get onto the system, and you will end up with a suboptimally sized system.
Yeah.
If, on the other hand, you try and load the first users, or let's call it the first user, an anchor tenant, to use a real property term, if you try and load all of the fixed costs on the anchor tenant, then it makes it difficult to get the project off the past sanction.
Yeah.
But our suggestion is that if the anchor tenant's project is state subsidised, then for societal reasons, the state should wish to see an optimally sized infrastructure system built, and therefore a cost distribution scheme which moves more towards loading the anchor tenant with cost is best from a societal point of view.
And that's reflected, is it, in, I think it was the slide where you had the 8 different scenarios. The one on the far left, I think it was scenario 1, was where you said that where the state took the lead on funding the infrastructure.
Yes, it's not specifically the state. It's that slide, the one with the 11 histograms, or the one histogram with the 11 scenarios. Yeah, option 1 is one where the two economies of scale are not shared at all. So the first mover, the anchor tenant, bears all of the fixed costs.
Yeah.
And as new system users come on, they are enabled to acquire system capacity at true incremental costs. So that reduces to a minimum the cost of capacity for follow-on users. Now, as the questioner rightly points out, that seems unfair on the anchor tenant. If you take a step back and look at it from a societal point of view, it's I think the alternative, or certainly at the other end of the spectrum, the costs for follow-on users will be so large that the thing will collapse into a project that only serves the anchor tenant, and that is not well, I would suggest that is probably not the right answer.
Okay, that's very helpful. On terms of, sorry, is there another? We've got a question here which is related. You showed a series of mechanisms of cost sharing, with 1 and 8 being opposite extremes. How do these compare with the existing gas grid charging mechanisms that you have in the United Kingdom and the NTS electricity charging mechanisms?
I think this is one for Johnny Hosford.
Johnny?
Good morning, Johnny Hosford here. I don't think these are directly analogous. at all, actually. My own background is in relation to the electricity transmission charges, where, of course, we're dealing with a significant amount of infrastructure which has already been built many years ago. In our case, in the UK, most of the high voltage electricity infrastructure was built between the late 50s and late 60s, early 70s. And that infrastructure, of course, is subject to very specific regulation itself in relation to charging, so that there are detailed charging principles that cover both connection to and use of system charges. So it's quite a different kettle of fish. Connection charges are based on the assets that afford a connection to the shared network for any individual user, and the use of system charges are basically smearing the cost of the interconnected system across a multitude of different users. And the way those charges are smeared is based on locational charging signals. For example, it's less expensive to connect generation to the system in a part of the system where there is a significant demand, and therefore the system needs generation in that area. Whereas if you're trying to add generation in a part of the system where there's already significant generation, and flowing from that there'll be potential bottlenecks in transmission, then it's a more expensive area to connect. So I think, in summary, this is not directly analogous to that, but the problem that we're trying to tackle here is how does one initiate a system of charging between users where you're dealing with the particular issues of establishing brand new infrastructure from scratch.
Yeah.
And that's what I think makes it really quite challenging, and why you see the very big differentials depending on exactly how that were done in terms of the proportion of those charges borne by the first mover versus the subsequent movers.
Okay, look, that's very helpful. We've got a question here related to risk. If SU1 does something to shut the system down, what compensation, if any, would be payable to the other users? Who pays and what are they compensated for? Lost revenue or just costs?
I think it's a very good question. It's a little outside the remit of the report. I think there's a whole, well, it would be a negotiated point, wouldn't it? I don't know if you've got any thoughts on that, Paul.
Happy to chip in. I mean, I think Johnny's point just before is exactly right in terms of it's not analogous, but clearly our history comes from a multi-user system background, and so things like constraint management, where there will be rules around how constraints are dealt with, I'm not sure it's particularly related to whether it's SU1 or SU3, if I get the numbers correct. I think the question is that on a shared user network there will be a set of conditions around how the network operates and how users are dealt with when problems occur. So it will come down to something like a set of general conditions that apply across the network to all users for things like specification and conditions of transport, for instance, and conditions of storage, that will then be applied equally as new users come on, and then there will be specific conditions for their individual connections. So I think, as Calum said, it's slightly outside the charging methodology specifically, but in the sort of general terms and conditions that will apply, things like constraint management will need to be dealt with, and they may be network specific, of course. So there may be particular features either regionally or even locally sort of within the UK where particular things need to be taken account of. So it's a little bit bespoke, I think, that one.
And not quite same, but on charges, can you say anything about how charges associated with a specific side branch of the system should be allocated? Should the whole system be treated as one for cost allocation, or should users pay specifically towards the side branches which they actually use?
If it's dedicated, user-dedicated infrastructure, then it would come under the connection charge in part 2, I think, of the report. The physical connection, at a point there will be a physical connection to the shared infrastructure that would need to be designed and constructed by the system operator. But again, it's a lot depends on what the regulation in the given jurisdiction says, but generally the costs of providing dedicated infrastructure or any infrastructure, whether it's physically attached to the shared infrastructure or not, should be allocated to the system user that has sole use of that.
Yeah. And one which you may feel is a little bit outside the terms of the report, but a finance question: how would the UK tax system feed into the described hypothetical tariff system? In particular, is there any complication introduced by the offshore ring-fence corporation tax rate?
Well, I know a little bit about this, but not enough to I know enough that I don't know enough to give an answer to that question. I don't know if Paul or Johnny feel they're in a position to.
Sorry, Paul Sullivan here. I think certainly outside of my comfort zone, but I wonder whether it's something to do with the storage medium. So when we're talking about hydrocarbons, there's a question, I guess, about tax treatment, hydrocarbon fields. When we're talking about saline formations where they're distinct from hydrocarbons, maybe it may not apply. So it may be bespoke, but yeah, certainly outside my comfort zone of this discussion, I think.
So look, that is outside the remit, but thanks for the question. And we're getting to the last minute or two, so just a final one. What are the circumstances where a user would pay for the construction, but then actually decide not to pay to use the capacity? May seem slightly counterintuitive, but perhaps you'd like to answer that one.
Yes, this is a point which often I'm often asked, and I think there's a number of areas, but two which are probably the primary ones. First of all, where state subsidy is used, clearly, or not clearly, but quite possibly, the state will not want to acquire the right to use the capacity which it subsidises the construction of. That's the first point. And equally, there could be other. It needn't be the state. It could be other benefactors, for what's the best term. And the second area is because of the economies of scale in large systems, it might be that a system user would, let's say, I don't know, a steel plant. Okay, just for an example, a steel plant might say, well, operator might say, well, look, I've got 20 years life left in my steel plant, and the cost of purchasing or procuring capacity in this system that's now being built, because of the economies of scale, is small enough such that I can pay for the cost of the infrastructure, but I only want to use it for 20 years. Now, the life of the infrastructure might be 40 years. That system user would then say, I'll pay the EPC charge and I'll pay the capacity rights charge for 20 years. Then the system operator would have to decide if it was indeed within its gift to decide, given the regulations in place, would have to decide whether it built that infrastructure capacity, the additional capacity, knowing that it would have to cover the costs of fixed OPEX at very least, and it would bear the demand risk, i.e. the risk that another user might not come up and take that capacity after the 20 years. So they're the two main areas where a party might be paying the EPC charge, but may not be paying any or all of the other two charges for the life of the asset.
Okay. Look, and I'm just going to squeeze one last question in about reliability, CO2 purity. As CO2 from different users is mixed clearly in the infrastructure, who's responsible in the case of contamination or other damage? How would that cost of that risk be allocated amongst users? Perhaps you can give a sort of quick, brief answer.
I think it's a very good question. It's similar to the previous question regarding responsibility if one user causes a shutdown of the system, sort of constraint charging and things like that. I think for me it's the same answer. I don't know if anybody else has anything to add.
It's David. I just broadly put in. I think it's anticipated that the system operator would issue a specification for CO2. Therefore, each user wanting to go onto that system would have to meet that specification to be allowed to enter their gas into the system. Is just a broad idea.
Okay, look, that's extremely helpful. Look, we've squeezed a lot of what I can see are really good quality questions in, and thanks very much to our panel for answering them. So, and thank you to National Grid, but in particular to Calum Hughes, Dave Bevan, Johnny Hosford, and Paul Sullivan, our panel this evening. Just a couple of points before I close up. We are committed to answering any outstanding questions. We haven't got any more time tonight. This webinar has been recorded, and the presentation slides will be put on the Institute's website in a couple of days. So if you've got colleagues who've missed it, please inform them that they will be able to go into those slides in the webinar, or indeed you might like to look at them later. So it remains for me to say thank you very much again to our presenters, and also to our questioners in the audience. Thank you for a good quality session. Feedback's always very welcome on these webinars, as well as suggestions for more topics. We've had a really broad series of webinars to date, and we've got more scheduled, so please check the website. What I want to do now is to thank you for your time, and I look forward to joining you again on another Global Institute webinar. Thank you very much.